Great.
Yep.
I see you on 2 meetings at
Awesome.
the same time.
Okay,
so-
I'm going to. I know. I'm trying it out. I'm trying to be. I'm trying to get my 2 of 5 things of working this week done at the same time. No, I've got. I'm able to open one on my computer, and one on my phone, so that way, it's not as much of a headache for Julia. I'm trying to make her do. Well, I don't think she has all the persons to do what that I have.
Well, I thought one of you is AI Joe and one of you is real Joe.
Yeah, it'd be funny if like one was like much easier to get along with and more intelligent than the other. That'd be like, oh, bring that other Joe to that meeting. It's like, oh, that's the fake one. Shoot, people like that one better. No, it's really me. I'm
You found a way
gonna
to
mute
clone
myself,
Joe, huh?
Julie. Yeah. I'm going to mute myself so that way I can communicate to the folks on the other line, on the other meeting.
Great. Thanks so much, Joe. Appreciate it.
Sure.
I'm going to appreciate your help with the letter too. So thank you.
Yeah, no problem. The good thing about that is if you invite the commander, maybe he's more willing to let me travel if he's going himself.
That makes a lot of sense.
That's good thinking, Kwong.
Yeah, it never hurt to invite the boss to the party you're
That's
going
right.
to. Right?
That's right. They're less likely to decline your travel if they're going, right?
Yeah.
Good morning, everyone, and thank you for joining the pre-workshop for the technical workshop for FIRO. I just want to make sure everybody's in the right place because we have two concurrent pre-workshops. These are meant to be more or less kind of a 101 and provide background information that will be helpful during the FIRO Technical Workshop. So this one is a deeper dive into the difference between a deterministic and ensemble forecast that Chad Hecht and Brett Whitin from the CNRFC and Chad Hecht from CW3E will be leading. Any questions concerning the logistical side of this in terms of being in the right pre-meeting or 101 for the FIRO technical meeting? The other one is on swims, and Jill Forbes is running that one. If you have questions, feel free to put them in the chat or raise your hand, just to make sure we're all in the right place. Okay, so hearing nothing, I'm going to hope that means that everybody is in the right place. And thank you for joining us this morning. A couple logistical things before I have the honor of introducing the two speakers this morning is we are recording this meeting, and this is really meant so for those that couldn't attend, it can be used and watched by them as a learning experience or to learn what will be covered during this time period. So do know that it is being recorded, and that is why. The other thing I will add is that this is meant to be interactive. So both the speakers, we've talked about this, we would like questions throughout. I will be monitoring the chat, or if you want to raise your hand, I'll be monitoring that and can provide, the space and time to ask those questions. So please do feel free to ask questions. It's really meant for everybody on the line to learn and get as much out of it as possible. So, and then with that, I get the pleasure of introducing our two speakers. And this morning we have Chad Hecht, who's a meteorologist and researcher with CW3E, the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography. And he is in an embedded position with the California Nevada River Forecasting Center and at the California Department of Water Resources, and has been at the center for 8 years now and is a very integral part of the forecasting and meteorology team for several of our FIRO projects. With Chad, Brett Whitin from the California Nevada River Forecast Center, we'll be talking, or I should have stated, Chad will be talking more about the meteorology forecast and how those are developed, than the difference between deterministic and ensemble. And Brett Whitin from the California Nevada River Forecast Center, has been part of many of our FIRO projects, and we'll be talking about how the California Nevada River Forecast Center develops their forecast and some of the uncertainty in the hydrologic forecast as part of FIRO. So with that, I think, Chad, I'll go ahead and turn it over to you if you want to share your screen and kick us off. So thank you.
Thank you, Julie. Are you seeing my screen? I had to use a web browser and I have not done that before, so I'm hoping this works.
Yes, I'm seeing your screen, but it's not in presenter mode yet. It's just the regular PowerPoint.
How about now?
Yep, looks great.
Awesome. Yeah, so I'm going to kick things off here, just kind of talking about the difference between deterministic and ensemble forecasts from the atmospheric perspective. I'll go ahead and start with a really basic overview of what an atmospheric model is, and then kind of dive a little bit deeper into deterministic versus ensemble, the benefits of it, and then apply it a little bit to one of the events that we had this past year that actually serves as a textbook example of why ensembles provide more of a benefit just versus looking at one solution pertaining to a forecast around an atmospheric river over California. And then I'll pass it to Brett, who's really going to dive deeper into the hydrologic forecasting, which, these are intertwined. The hydrology is driven by the atmosphere, but there are a lot of nuances that lead to the outcomes or prediction leading up to an event across the Western United States. So with that, I'll go ahead and start again with the what Meteorology 101 with what is an atmospheric forecast model. Just to kind of keep it simple and not get too deep into the weeds, an atmospheric forecast model is just a computer algorithm that uses mathematical equations to predict the atmospheric conditions. On the surface level, or really just keep it basic again, is an atmospheric model typically starts with as many observations as it can really get its hands on and assimilates it to create a grid-based representation of what the atmosphere's current state is, and then uses differential equations to kind of propagate through time and space what the atmosphere is going to do based on these differential equations and these fluid models. Atmospheric models tend to be on a gridded, or they are on a gridded kind of map on both the horizontal and the vertical, where it has variables like your temperature, your humidity, pressure, moisture fluxes, and different radiance balances or fluxes. And then as you step up into the atmosphere, you can introduce things like aerosols and cloud cover. I mentioned that it really assimilates as many observations as it can, and I included a product from the ECMWF in the bottom left here that shows all the aircraft observations that were assimilated into, I believe this was the 0Z run from a couple of days ago, but it just goes to show just how many observations do get assimilated into an atmospheric forecast model, whereas there were 175,000, nearly 176,000 aircraft observations alone, and this is just from commercial aircraft. This does not include your surface-based meteorological stations, your balloon launches, the satellite observations, your buoys out over the ocean, and things along those lines. Obviously, we do know that the oceans are a data sparse region of the globe, and therefore atmospheric river reconnaissance is such an integral part to predicting weather on the west coast of the United States, just because everything upstream of California, Washington, and Oregon is the Pacific Ocean, where you don't get observations from the surface outside of your buoys and your satellites, which do have limitations, and therefore can lead to a lot of uncertainty as these systems evolve across the Pacific Ocean. The types of atmospheric models range from the global to mesoscale down to the microscale. I provided some examples of these different types of atmospheric models, whereas your global models will be your NCEP global forecast system, your GFS, and your ECMWF, which kind of give you a forecast around the entire globe. And then you have your more regional forecast models, or your mesoscale, which can cover, continental down to more, say, just the United States by itself. Some examples of the mesoscale models would be your high resolution rapid refresh model, or your HER, your North American model, your NAM, or even the West Wharf could be considered a mesoscale model or regional model. And then your microscale can take that even down further with your higher resolution, your more local forecasts, where some examples of that would be to run a high resolution West Wharf or a high resolution WRF weather research and forecasting model, or your model for prediction across scales, your MPAS. These microscale models can be used to forecast things like microclimates over a city, or even your mountain meteorology over a specific mountain range, where you can get really high resolution forecast models. There's pros and cons to each of these kind of types of atmospheric models, whereas if you wanted to run a high resolution forecast, that's going to that will require a lot more compute power, and therefore it tends to not go as far out in time, whereas your global forecast models do run at a lower resolution in terms of the vertical spacing at which you are able to see specific points in the atmosphere, but they do tend to go out much further in time. And same with your mesoscale models, is like it's a cost benefit analysis of how much of the atmosphere do you want to be able to see, and how much of the, say, topography do you want to resolve. You tend to have to kind of bring that how far out in time you can see just because of the compute power and the cost benefit between all of these different variables when running certain types of models. So I wanted to get into the reasons why when we look at, say, a deterministic forecast, why the models can differ. Obviously, there's differences, say, between the ECMWF and the GFS, your two most popular global models. In the resolution, all models use kind of a different algorithm to not only predict what's going on, they tend to use similar equations, but there can be differences in the exact processes that are used to kind of project what's going to happen in the future, but there's different algorithms in the data assimilation as well. The initial conditions accuracy with the kind of assimilation of all of these observations into the model to kind of get where the model thinks what's happening right now, those processes can be different, which the initial state can lead to kind of your chaos theory where the further out in time you step, the more these models can diverge and can lead to quite substantial differences in the forecast model.
Chad,
did somebody raise their hand?
Sorry. Yeah, Brett raised his hand. I wanted to give him a chance to comment.
Hey, yeah, Chad. It's probably a good slide to ask the question on, but also you talked about earlier is observations. Say, for example, the global models like the EC and the GFS, do they use the same observation networks essentially, or are they quite different in terms of what they use as observations?
I don't know the exact specifics on, if there's a specific observation that the GFS uses versus the EC. I know they all have algorithms in the terms of what observations they do assimilate and throw out versus like what it thinks is good observations and bad. I believe Anna's on this call, and I know has worked with getting data assimilated into some of the global forecast systems and might have some insight into this. I don't know, Anna, if you had anything.
Yeah, I think that it is a little bit different what each of them kind of assimilate. I know that they're all assimilating things like dropsondes. I also know that even in terms of like the radiosonde and upper air stuff that ECMWF has asked in some of our meetings, like if there's any chance of that coming back. They also used to assimilate profiler data. So I think it would be really nice to get like a catalog of who's assimilating what and who would like to be assimilating what, so we can have a really strong sense of that. Another thing that happened during AR Recon is that the American model wasn't assimilating the buoy data, and now that's been resolved as well. So I think like in general, they're all assimilating similar things, but they all have differences too in kind of like what vertical resolution they can take. Can they take radiosondes and dropsondes with just the mandatory and significant levels versus the full resolution data and all of that? So not a super satisfying answer, but I think the answer basically is that there are differences, and knowing what those are in a more specific sense could certainly be helpful. So I don't know if that was helpful or not at all, but thanks for the opportunity to chime in.
Yeah, thanks. That was helpful. Yeah.
Another good example of kind of a difference would be like the HER, which was developed for like mesoscale forecasting and severe thunderstorms over the plains for the most part, does assimilate in real time radar data to try to, say get convective organization right. So that's another example for one of the mesoscale models versus the global. I don't believe the GFS or EC assimilate like the actual radar reflectivity from say the WSR 88D network.
Great.
So kind of yes. Sorry, Brad, did you want to say something?
We're just saying thank you. That's it. Thanks.
No worries. Yeah, no worries. Thank you. So kind of continuing on, again, there's many reasons why, say, deterministic forecasts or even ensembles can lead to different solutions. And the graphic I provided on the right was kind of this is the event that I'm going to kind of focus on as we go through some of these examples of the deterministic versus ensemble. And this was an example where the GFS and EC differed very substantially at 186 hours, with the GFS forecasting somewhat of an extreme atmospheric river into California, and the EC had a northwesterly AR. And this is an example of the two global models differing to such a substantial extent. And some of those reasons could be, data assimilation, the algorithms at which they assimilate that data, and then the chaos that kind of gets introduced as you step through the forecast out to 186 hours. Any questions about kind of what an atmospheric model is before I move on to the differences between deterministic and ensemble? All right, not hearing anything. Moving through to the deterministic versus ensemble. So I mentioned the different types of atmospheric models ranging from the global down to the mesoscale to the microscale. I want to get into the differences between the deterministic versus the ensemble, and the GFS and the EC by themselves are the two deterministic global forecast models that are used quite widely throughout atmospheric science. But deterministic forecasts only give you one forecast. The benefits of that being that it's clearer and easier to interpret versus numerous different outcomes. But the problems with a deterministic forecast is that it only gives you that one solution and lacks the uncertainty or the statistical probabilities that are necessary when making decisions using atmospheric variables. Ensembles bring in that uncertainty by providing multiple solutions to the same outcome or to the same event, say, and accounts for that uncertainty and gives those probabilities. But maybe a con to that would be that they're more difficult and complex to interpret. They require maybe, say, more data visualization to provide a useful forecast for, say, precipitation in the Western United States. Ensembles are typically created using numerous methods or numerous different kind of, whether it be initial condition and or perturbation or physical processes to lead to these different outcomes. But it runs essentially multiple, say, deterministic forecasts using the same forecast system to lead to these different solutions that will then provide that uncertainty leading up to a particular event. Some ways in which these ensembles are created are, say, perturbed parameterization schemes. That's essentially taking the initial conditions, perturbing some of those, and then running the forecast model using those perturbed initial conditions to therefore increase the uncertainty based on those observations by themselves. A different method used to create ensembles is stochastic parameterizations, and that's kind of like just changing the physical characteristics of the model, say the convective parameterization, which then will have a handful of members that change the interaction between the boundary layer, and therefore will introduce a couple of solutions where the model is assuming certain things that lead to a different outcome versus, say, just a deterministic by itself. Or you can have something like a multi-model ensemble, which just kind of combines numerous different models that lead to multiple outcomes for a given forecast. And I provided some examples of an ensemble forecast in the bottom left there, one being, say, your hurricane track forecast, which is quite popular over the eastern United States to provide some uncertainty into where exactly a hurricane might make landfall and at what intensity. And then I provided one of the products on the CW3E website of the watershed precipitation, combining the ECMWF ensemble prediction system, or EPS, and the GEFS, the global ensemble forecast system. And to really get into a reason why ensembles are quite beneficial, I wanted to use the event from this past late March and early April to show when deterministic forecasts were really quite different, why the ensembles provided that additional information to kind of show the benefits of looking at the spread of a potential event. This event, again, I'm going to use the forecasts that were initialized at 0 UTC on the 26th of March for a landfall period around the 1st or 2nd of April, where the GFS was really quite bullish for an atmospheric river into California versus the EC was much less so and had more of a northwesterly AR, which would not be conducive to heavy precipitation over California. This is the deterministic forecast I'm showing here, where on April 2nd or the period valid at 12 UTC on April 2nd shows the ECMWF has a northwesterly AR conditions over central coast of California over top of high pressure. Or if we look at what the GFS deterministic was forecasting, had nearly an extreme atmospheric river with IVT greater than 1,000 units moving onshore over Northern California into the Bay Area. To get a closer look at those differences.
Sorry, Chad, to interrupt. You just mentioned UTC. Do you mind just taking a minute? Some people may, but just in case, to make sure everybody understands what UTC is and why forecasting is used that instead of
UTC or
local time.
Yeah, UTC is universal, or it's also Greenwich Mean Time. It's at the 0 degree meridian over Western Europe. It's just so when forecasting, everybody's on the same page around the globe. It's Z time, Zulu. It's used militarily as well. For California, it's right now we're 7 hours back, and in the winter time we're 8 hours back. So 12 UTC on April 2nd would be 4 a.m. This is actually past daylight savings. So this would be 5 a.m. local time. And this just keeps all models on the same page, all forecasts kind of relatively on the same page. It's just a way to keep everything consistent and therefore apples to apples across the field of meteorology, but also for numerous different entities around the globe as well. That a good explanation, Julie? Yeah. Good.
Perfect. Thank you.
Yeah. So again, kind of going back to this forecast for 5 a.m. local time, April 2nd, looking a little bit closer, just giving another example of the GFS predicting an event that would be quite impactful for California at 180-hour lead time versus the ECMWF, or the European deterministic forecast, not having an event that's nearly as close to what the GFS is suggesting. So if we were going or making a decision just looking at the deterministic forecast, these two solutions, just the deterministic, are very different in terms of the decision making that needs, or the decisions that need to be made on the ground in Northern California at 180 hours prior to the event. And the atmospheric river forecasts were quite different, but also the precipitation forecasts were quite substantially different, where the GFS on the left here shows forecasts above 7 inches across the Sierra Nevada and the Coast Range over the South Bay, where the ECMWF was forecasting not nearly as much, down to about 1.5 to 2 inches in some locations across Northern California. So the decisions that need to be made based on these two forecasts would be quite different, and therefore you need to bring in additional information, and that's why ensembles provide that information to, not to make a brash decision based off of just the GFS alone. And one of the ways in which we at CW3E bring in the ensembles is one of our most popular forecast products, which is the AR landfall tool. And again, this forecast was initialized at 0 Z on the 26th of March, forecasting just after April 1st the probabilities of AR conditions over, say, central to northern California, the GFS deterministic was showing an extreme atmospheric river greater than 1,000 units of IVT in the northern California, but looking at the probabilities of just 250 units over California, we see that it's not nearly as confident of AR conditions. With probabilities, greater than 80%, it is still, high probabilities at a 7-day lead time, but it's not like nearly as confident of an extreme AR into Northern California. And if we look at the European ensemble system, it was even less confident that there were going to be AR conditions over California. And just starting with this ensemble forecast for this event, this kind of leads me when making a forecast to dive deeper to see what the probabilities of AR conditions are over California and what do those AR conditions look like and what does that mean for the precipitation forecast. So looking at the IVT plume diagram for Northern California, it's 37 degrees north. This is plotting a time series of each individual ensemble from both the GEFS and the ECEPS. And the green dots here denote where the GEFS thinks IVT will peak in this window, and the purple dots are where the ECEPS thinks IVT will peak and at what magnitude and time. Looking at the clustering of green dots, we see that there's about 13 or so GEFS members that are peaking above 750 units, sometime between the 2nd and the 4th. So a lot of uncertainty in the timing of that strong plus magnitude atmospheric river. The EC, I talked about how the deterministic product from the EC was not nearly as bullish for an atmospheric river, but the ensemble does have about 3 solutions within the 51 member ensemble above 750 units. So while the deterministic doesn't really have much in terms of that strong plus atmospheric river, the ensemble does have 3 out of the 51 members agreeing more with the GEFS, but the ensemble uncertainty here shows me that the deterministic forecast might be one of the most bullish solutions in terms of all of these potential outcomes from the ensemble system and all of the deterministic products. And then we also can bring in the precipitation information and compare the GFS deterministic to some of the solutions in the ensemble spread and compare it also to some additional deterministic products. Whereas looking at the upper Yuba River 7 or 10-day accumulation, we see that the GFS, just like the deterministic IVT forecast, is the most bullish product out of all of the other deterministic products and ensemble products as well. The ECMWF is the lowest in terms of these products that are listed here. The NBM, which is a statistically post-processed product that brings in pretty much every operational atmospheric forecast model, is leaning more towards the GFS, but is likely hedging its bets at this point at long lead times. We see that the GEFS ensemble is much lower than what the GFS is forecasting, which over the upper Yuba was at this time forecasting 8 inches of watershed average precipitation. But then we can also look at the ensemble spread within the GFS alone, which is the kind of reddish pink tracers here, but also the box and whisker plot on the right. Again, the deterministic is forecasting 8 inches of mean aerial precipitation, which is well outside of the interquartile range of the GEFS spread, which again tells me the deterministic model is likely is not nearly as statistically probable when bringing in all of this ensemble information. And we see that the ECMWF ensemble system is even lower than the GEFS, but the means are much closer than the deterministic products are by themselves.
Chad, real quickly, there's a question in the chat about what's the differences.
Yeah, but go ahead.
Sorry, there's a little bit of delay in speaking. Sorry about that. There's a question in the chat about the differences in configurations of the GEFS and EPS that would lead to discrepancy in the forecast.
Yeah, so
specifically.
Precip specifically, there's numerous reasons why you can get to that point, and I started a little bit with the introduction of atmospheric models, where there's differences in the data assimilation, which kind of starts that process where they can begin to differ. They handle different physical interactions differently, which as you step through a forecast can introduce even more uncertainty, and it kind of snowballs on top of itself. And then when looking at the ensemble systems comparatively, there's differences in resolution between the two of them. You get higher resolution from the European system, which that can introduce differences because it gives you not necessarily a better look, but you can resolve maybe finer scale features, which can lead to differences in the forecast. And then another difference between the two ensemble systems is that there are more members within the ECMWF. There's 51, whereas the GEFS has 31, and therefore the statistical distribution or the output between the two, one could be better dispersive or more dispersive or over dispersive, and therefore that could lead to one being better than the other. Obviously, it's an event by event basis, but those are some of the reasons why the ensemble systems can predict certain outcomes versus the other.
Thanks, Chad.
Yeah. Any other questions about atmospheric forecast models, deterministic versus ensembles? Really delayed.
Chad, I have one more question. Amongst the meteorology community, is there sort of rules of thumbs for knowing which model to trust more in certain situations, and how robust are they?
Yeah, so that's obviously, it's relatively well known that the EC performs better than the GFS, but we can point to specific examples where the GFS does beat the EC. And there's consistent changes throughout, over the years that kind of changes that performance between the two. I can think back to one event over California back in 2019, where the GEFS system provided much longer lead time than the EC. But general rule of thumb in the community of meteorology is that the EC performs statistically better than the American system.
Great, thanks, Chad.
Hey, Chad, and I guess the MBM is supposed to take advantage of all that, right? I mean, it's going to be weighting the various atmospheric models based on, I guess, a variety of things, but skill being one of them. And so hopefully the MBM would be kind of utilizing each model and their strengths appropriately. Maybe
Yeah,
not
that's correct. Yeah, and that changes run to run too, I believe, depending on it. So the NBM does look back. I forget exactly if it's 30 or 60 days and performs kind of bias correction. And that changes exactly what model it leans on the most heavily. I remember a couple of years ago looking deeper into it, does seem like it leans more heavily on the EC, but again, that can vary depending on the past 30 to 60 days.
Yeah, and as we saw this winter, that short period of 60 days or 30-day look back may not always be a good, I guess, sample size to do any bias correction. We saw some.
Yeah, that's the issue with California is sometimes in that window you only have one event, and in this past winter, that one event was heavily underpredicted over the north coast of California, and led to some interesting forecasts from the NBM for some of the events in December and I think even January. It was trying to essentially overcorrected itself.
So Patrick has a question about the 10-day precipitation. I can actually take a stab at this, Patrick. He mentioned the QPF webpage goes out to day 10, while some of these models go out beyond, and the reasoning for only going out to day 10. Patrick, it's generally because the skill drops off so substantially. We've seen it, after day 7 and then day 10. And then they're just not very many models. There's only 2 really that go out beyond day 10. And so the combination between the drop off in skill and the few models that go out that far is why we decided to drop it to keep it at day 10. And I think in general, like the landfall tool and the plume diagrams go out for the longer lead times. And this is some of the subseasonal work too goes out in week 2 to those longer lead times. And thinking about it a bit more as a situational awareness of what might be coming, but putting exact numbers on it because of the drop off in skill, we were a little hesitant to do that. And I think back to you.
All right. So hopefully that was a constructive overview of the atmospheric models and why deterministic can vary quite substantially, but also why ensembles are important. But atmospheric models are quite different than hydrologic models, and that's why we're going to pass it to Brett to kind of cover some of the work done at the RFC and how the hydrologic forecasting can differ, or how hydrologic forecasting differs from meteorological atmospheric models.
All right, thanks, Chad. Yeah, I think what I'll go over is, how we generate deterministic forecasts at the RFC in terms of stream flow, and how the ensemble forecasting is a little different from at least the methodology compared to some of the atmospheric ensemble modeling that's done. So I guess first off, we'll talk about deterministic forecasts and how those are done at a river forecast center. Specifically, this is really just specific to the CNRFC. So, we basically input the meteorological forcings into the hydro models. So in the observed, we run our models in an observed period of time, and then also obviously in the forecast period. So for the observed, we have a mean area precipitation, which is a quality controlled precipitation estimate for each basin, and that's based on really just a forecaster going through and quality controlling the gauge networks that we use on a 6-hour time step basis. And then from those point estimates, the grids are created, and then obviously mean aerial precipitations estimates are created. We do have an automated program called MRMS. It's just sort of a backup in case for whatever reason we can't generate our quality controlled precipitation estimates. But we haven't really utilized the MRMS, and it's a good thing, I think, because there are differences, pretty big differences sometimes between those two observed precipitation estimates. And really what it comes down to for hydrologic modeling is you want to be consistent between what you're using and how, and the forcings for what you calibrate the model to with what you're using in operations. You don't want to introduce much bias if you can help it. And so, you know, the MPE sort of methodology is really what's used also in model calibration. So we want to be as consistent as possible when we go into operational forecasting, that we're using that same procedure to estimate precipitation. Temperature is pretty much an automated product that we bring in, basically RTMA. Freezing level comes from the HER model that I think Chad mentioned as one of the atmospheric models. Now for the forecast, yeah, so the precipitation forecast is that we use in our deterministic forecast comes from our HASI and our meteorologists, where they're looking at a variety of atmospheric models and coming up with their best estimate of what they think the precipitation will be out to day 6. And our deterministic forecasts that we put out on the webpage for streamflow only go out 5 days. We do put 6 days out for precipitation, but in our modeling system, CHIPS, we do run it out 10 days just to have a little bit more lead time to kind of see what's going out in days 7 to 10. And that's just an automated output from the MBM, which is brought in a grid format into our CHIPS modeling framework. And then mean error precipitation is created from those grids. Temperature is from the NBM for all lead times. And then freezing level, again, is something that the HAS unit at the RFC generates. So it's a manual sort of process where they're looking at, usually it's a mix between the GFS and the European model. And that goes out 10 days. So freezing level is really what's used in our hydro model to decipher where it's raining and where it is snowing. And so that can be pretty important depending on what watersheds we're dealing with. Next slide. Okay, there we go. So I mentioned CHIPS. So CHIPS is really just sort of a GUI visual interface that we use to do our hydro modeling, and basically have a lot of hydrologic modeling components within CHIPS that we can use. So Snow 17, SAC SMA are our snow and soil models. This is we ingest all of our meteorological forcings into this framework and process them all through the hydro models, and ultimately generate streamflow forecasts, both deterministic and ensemble. Next slide. I must be getting a lag here. Okay. So let's talk about ensemble forecasting in the hydro world at the RFCs. So we basically generate meteorological ensembles using a meteorological ensemble preprocessor. And once those meteorological ensembles, both precipitation and temperature, are created, we run them through the same hydro models that the deterministic forecasts have been run through. So the initial conditions, all the assumptions on runoff processes are all computed the same way, both deterministic and ensemble. The only difference are the meteorological inputs. And so we generate ensembles based on a deterministic input into that ensemble generator. So that's what's a little bit different from, say, an atmospheric model ensemble. Those are ensembles that are generated by perturbations in the atmosphere that Chad talked about. But in terms of HGFS and how we run that through the hydro models, it's more of a statistical process. So, and based on the uncertainty around deterministic forecasts. So for precipitation, days 0 to 6, are based on the uncertainty in the QPF coming out of the RFC. And then beyond day 6, out to day 14, it's uncertainty in the GFS mean. And then for temperature, it's really an uncertainty in the HAZ temperature forecast, which essentially is coming from the MBM, out to day 10, and then from 11 to 14, it's the GFS V12 mean. Beyond days 14, there's really no use of the weather model, atmospheric models. It's really just based on pure climatological spread. So just taking historical temperature and precipitation for a climatological period. So 1980 to 2022 is what actually it's 2023 now. So this is an outdated slide. Next year will be 2024. We keep adding one member in our climatology every year as we go forward in time. And we run those ensembles going out 365 days. So we run those ensembles every morning to go out a full year. When we do updates during flood events where we're issuing forecasts outside of our morning issuance time, we're only going to run those HFS streamflow forecasts out 30 days. We can get them done quicker that way. And also, it's just the value of adding, a 365-day run 4 times a day just isn't really there. So, so we've shortened those HFS run times, just lead times, just to go out to 30 days for non-morning HFS issuances. And I'll just point out, so the deterministic, we've tried, at least at CNRFC, to try to add coherency between, the meteorological inputs that are going into the deterministic and then also what's going into the ensembles. So, the deterministic forecast goes out 5 days. So, the QPF and the temperature that's run through the hydro models for the deterministic is the same inputs that go into the ensemble generator for the HFS output. So there is some coherency, at least in terms of the meteorological inputs there between the two products. Next slide. Oh, Chad, do you have your hand up?
Yeah, I'm super delayed, and that makes it bad to drive the PowerPoint. Julie, could you download it from the email real quick and let me know when you're ready to switch off for Brett?
Yes, we'll
Oh,
do.
do you? Okay. So you want me to keep going for now, or just wait?
Yeah, go ahead.
I think you should, yeah,
Okay.
keep going. It's not so bad, but I will work on it on this end.
Okay. So I'm going to just touch upon really generally, how ensembles are created. I did mention it's more of a statistical process, and it's really done. The parameterization, the uncertainty and forecast error sort of calculations that are done, parametric distributions that are calculated, are done offline. These aren't done in our operational forecast system. They're done typically like once a year, and what happens in that parameter estimating process is you're basically comparing forecast to observations, whether that's temperature or precip. We do both, and so we do that comparison over a period of time where we have a collection of historical forecasts and observations. And so, for example, the first 6 days of the precipitation forecasts are based on the RFC QPF. So we have an archive of from 2010 to 2023, essentially, is what we've used for this water year, those pairs. So for all different lead times going out to 6 days, we have, for every watershed that we model, we have both a forecast amount and a precipitation amount, and an observed precipitation amount that we can compare and generate parametric distributions from. And so then in real time in operational forecasting, when we have a precipitation forecast, we refer to these distributions to then sample from to generate precipitation members that fit within that distribution. And so this is done for, like I said, for both temperature and precipitation for all watersheds. And so these comparisons are done at the watershed level, not a grid level, but a watershed level that we model. So I said we do update these once a year. We actually did update them twice a year this year. I think it was sometime in March, maybe, or February, where we changed the input source for the temperature to go from GFS to the RFC temperature forecast out to day 10. Especially during snowmelt season, there's some confusion. And again, this goes back to coherency where, snowmelt is driven mainly by temperatures. And the ensembles were using the GFS uncertainty for all lead times, but our deterministic was using the MBM. And so, sometimes the deterministic would be, very bottom or very top or, even outside the spread sometimes. And a lot of it we were speculating had to do with the fact that the deterministic was using one source of temperature forecasts and the ensembles was using the other. And so we basically use the same inputs for both deterministic ensemble. And from what I've seen so far in snowmelt season this year, things are looking a lot better in terms of where the deterministic sort of falls within the spread of the ensembles. Next slide.
Brett, I think Chad and I are going to real quickly try and switch running the show. Hopefully there will be less of a delay, but
Sounds good.
Okay. Should be seeing this and then. Oh, are you seeing I think you're seeing the wrong one. Oh, are you seeing the right one now?
Yes.
Okay. I will say,
All right,
Chad, can we switch and have you monitor the chat? Because with Teams, I don't see it anymore.
Yeah.
Great. Thank you.
So the next slide here, just a summary that I've kind of touched upon in previous slides, but it just kind of goes over the overall modeling flow chart of how we do things to get stream flow forecasts out. We have observed precipitation, temperature, and freezing level. We also rely on observed river gauges and pool elevation gauges and things like that. They also get brought into the hydro models. And then obviously the precipitation forecasts as well. They all get processed through a variety of hydro models that I touched upon before, Snow 17 and SAC SMA being the primary ones for snow and soil moisture runoff modeling. But we also have, hydrologic routing, reservoir modeling, rain snow elevation, which basically translates a freezing level into a rain snow line. Those all get processed through the height, and ultimately a stream flow forecast is generated. I guess I probably should also mention that the ensembles, one difference in terms of the meteorological inputs, we do capture uncertainty in temperature and precipitation in the ensembles. We do not capture uncertainty in that rain snow line. So we don't have that capability built into the HFS system yet. They're working on it at the national level in the Weather Service, but that's not going to be available for probably, I would say, 6 months to a year. So what we assume for freezing level in our ensemble forecasting is the deterministic forecast freezing level going out 10 days. And after 10 days, it's pure climatological freezing level uncertainty that's used from days 11 onward. So that's how we kind of deal with freezing level now. Next slide. So now I'll just really focus on hydrologic uncertainty. Right now, we do not capture any hydrologic uncertainty in our ensemble streamflow forecast. So it's all meteorological uncertainty. which is, the more significant factor typically. But I thought I would at least touch upon some of the uncertainty that we have in hydro modeling that we are not capturing. There is a component to HGFS called ONSPOS that can account for hydro uncertainty. We tested this out many, many years ago. It didn't seem to be valuable when we were looking at it. We're going through right now at a national level to reevaluate it again. But there's also a lot of research going on to look into other ways to capture hydro uncertainty in the research community. CB3E is looking at ways of doing that as well. So I'm hopeful that we can get there in the coming years to capture hydro uncertainty, at least some of the hydro uncertainty, maybe not all aspects, in the next few years. But we'll see where that research goes and funding streams and so forth. Uncertainty there as well. So we'll go ahead and, well, I guess I'll just mention, so obviously watershed state uncertainty, what the soil moisture is, snowpack, those sort of things are factors that go into, runoff response and not knowing exactly what those are. Also sort of the timing and shape, the hydrograph, how the rainfall is distributed within a basin sometimes can affect how fast it comes off, and what that shape of that hydrograph looks like. There's also hydraulic effects, right? There's backwater, there's levee breaches that could happen, channel changes, even through an event, very active movable bed channels. Rating curve uncertainty, which kind of goes into channel changes as well. Travel times, sometimes travel times can change throughout a year. They're not always stagnant. So that's a variable. And obviously regulation from reservoirs, that's an uncertainty that we don't capture either. So I'll just go ahead and step through some examples of some of these on the next few slides. Go ahead and go to the next slide, please. So here's an example of Ukiah, actually. And what this is this is showing a historical simulation. So this is in the past, not a forecast, but it's showing the observations out of our CHIPS modeling system in red. So those red dots are the observed hourly flow values at Ukiah for, this looks like it was back in March 2025. The blue is the model simulation. So as you can see, the timing is a little bit faster than what came in and a little bit underdone. And so, RFC forecasters have a lot of tools at their disposal to modify so the hydro modeling. So we can modify, for example, the hydrograph, and that's what I did here in this example. So if we go to the next slide, I made a slight change into how the runoff is happening in terms of hydrograph, and you can see how the timing is now a little bit better on that first big event, and it also making that change on that first event also improved the timing of the second event. So sometimes if you have an event in the past and you have another event into the future in the forecast, you can make that change, and the assumption is that that change would also, you also have confidence that that change will be good for the future event. And so this is the case where we had two sort of rises at Ukiah, and making the change on the first one, if that was in the past, and let's just say the second rise was in the future, you would be adding some model improvement over the default by keeping that hydrograph mod in place for the future event. But again, this is not something that's captured in the ensemble uncertainty right now with HGFS. Go to the next slide, please. River routings is another one. So this is another historical simulation out of CHIPS showing Healdsburg on the Russian River. And so what we're showing here, again, the observations are those dots in the red sort of orangish line. The the total flow simulation at Healdsburg is the blue. And then all these other hydrographs are just the components, the routing components that are coming into Healdsburg. So you've got, sort of a local flow for that watershed. You have probably the biggest contributor is what's coming in from upstream, which is that lighter blue. And so obviously we're seeing that the model is routing things a little bit too fast and probably not attenuating things quite as much. And so if you go to the next slide, I made some changes to the hydrologic routing. So the variable lag K parameters. And so I basically lagged and also attenuated what's coming in from upstream into Healdsburg and got a better match the peak. And so, that's another one that sometimes if you have an event in the 10-day window that you're in the past that you're looking at and trying to line up observations with the model simulation better, that can improve your forecasts in the future. And a lot of times, like for the beginning of the water year, for example, in October, November, when you first start getting a first few events, sometimes things can be a bit slower than later on in the winter. And so you'll want to make some changes early on, and then maybe remove those changes once you get into the winter and travel time starts speeding up. But there's a variety of reasons why you might want to change them and why you want to keep them or not keep them. But again, this is something that is a factor that plays into forecast error that is not incorporated into the HEFS because it's a hydrologic uncertainty factor. Go ahead to the next slide. This is an example of an event that happened this water year on the Pitt River. We saw really significant flow up on the Pitt. We saw above major flood stage. So really, really high flows. And one of the biggest drivers of uncertainty was the low level snow that was out there in this watershed, and then the rain on the snow adding to the runoff. Sometimes that low level snow is a really hard, parameter to get a handle on how much is really out there. And if the graphic on the left is showing, how high the river actually got, which is the blue, and the forecast for this particular day, February 3rd, is the green. And so we underdid that forecast. And if you look up on the top, that's the precipitation that fell. So the precipitation that fell is the blue little dashed lines. And then the precipitation that was forecast on February 3rd is the green little dashed lines. And so you can see that the precipitation forecast was actually overdone. So we actually got less precipitation, but the runoff was greater. And then the biggest reason why is that there was a lot more snow melt happening. That low level snow melt was happening that we were underestimating how much low level snow was out there. So it's a tricky thing to really get a handle on sometimes, because there's no gauges out there that are really telling you, snow tells and other things that are already telling you what that low level snow estimate is for some of these watersheds that are very susceptible to rain on snow. So again, not incorporated into the HFS. And if I show the HFS here, it would not look good because it was really out to lunch because it didn't incorporate one of the more dominant factors in this event, which was the hydro uncertainty and how much snowpack was out there. Go to the next slide. Now I'll get into another situation. This is pretty unique to some of the rivers in the Central Coast, but so this isn't necessarily a significant factor in every river that we model, but it definitely is in the Pajaro. So this is just a graphic showing the watersheds that we have for the upper Pajaro River. This is the San Benito. We have a few forecast points within this network. San Benito near Willow Creek, and then we have a pretty big tributary coming in below San Benito near Willow Creek called Tres Pinos. and further on downstream is San Benito at Hollister. And so this event was in 2023. We were coming out of a pretty significant drought. And we had a really significant precip event that happened, and we ended up getting flooding on the Pajaro. And so I want to just step through some of the model simulations that we had for these particular locations that were pretty surprising to everyone that was involved with the forecasting for this event. So go into the next slide here. So this is got a lot of information on it, and I'll try to explain everything here. But this is the forecast for Hollister. So this is the downstream point in that graphic I just showed. And so Tres Pinos is the big tributary that comes in between the upstream location at San Benito and the downstream at Hollister. And what we saw down at Hollister was a lot less than what we were modeling, assuming complete volume conservation from upstream to downstream. So the red dots are the observations that occurred at Hollister for this event in 2023. And Tres Pinos, that big tributary that comes in between, basically that water just never showed up. So the total flow, if you assume 100% volume conservation, that total flow should have been somewhere around 5,500 CFS. What actually came in was probably around 2,500. So a significant volume loss, theory being that a lot of water broke out into the floodplain and just sunk into the ground. And that's a difficult thing. Those deep groundwater losses are a difficult thing to model. And so we just weren't able to capture that volume loss in our hydro modeling. So it didn't necessarily behave that way for other events that happened later that year, like in March. But because we were coming out of a drought and groundwater tables were pretty low, that this amount of volume just was lost between the two reaches on the San Benito. Go to the next slide. And here's another example of sort of volume loss that can happen that is hard to model in the hydro models. This is on the Salinas. Again, this is from 2023, happened in January. So the upstream point on the Salinas here is Bradley. And so Bradley flow was routed down and added to a local flow to come up with a total flow on the Salinas at Soledad. And so that's what this picture is of the observations that show those red dots. That's what happened at Soledad. Again, if you assume total model hydro model conservation, you would have something significantly larger. We do have some capability to estimate like channel losses, and we have some of those for the Salinas. And so that's why our total modeled flow at Soledad here is that blue line. It's about 30,000 CFS, which is less than what's coming upstream from Bradley, which was about 37. So we were, based on the model calibration that we did, we know that there's volume loss going on there. It's a very sandy, unconfined aquifers going on, and we know that there could be a lot of channel loss. But the extreme drought that we had coming into this water year was something that we weren't able to model well. And so, water broke out between Bradley and Soledad. It went into the floodplain. They're not called levees. They're called, I can't remember, berms, something like that. Berms broke, water got out, sunk into the ground, and never came back into the channel. And so we saw significant volume losses. And so we had some over predictions for flood forecasts in the lower reaches of the Salinas until we could get a better handle on those volume losses. So Again, this wasn't as significant for the March event, but it was for the January event 2023 because it was really the first big event of the water year coming out of the big drought. So these are things that, you know, it's really hard to capture in a hydro model, and it actually would be pretty difficult to capture this in a hydro model uncertainty with ONSPOS, the current sort of tool we have to try to emulate hydro uncertainty, and that's one reason why we don't use it. Go to the next slide. So rating curves, obviously, you know, we all know, I think, what a rating curve is. It's basically relating flow to stage. So for all of our flood forecast points, ultimately what we want to do is estimate a stage. But the hydro models are modeling flow, and so we need to make that translation from flow to stage. And every point is a little different. Some channels are a little bit more stable, a little bit more less uncertainty in terms of that flow stage relationship, but there is uncertainty. If I was to show you these on the Salinas, you would see much more spread because it's their sandy channels. You can get a lot of active, you know, bed movement throughout an event, deposition and scour. This is for Hopland, so a much more stable channel. But even this, you can see, you know, there is some decent spread in that flow stage relationship for a place like Hopland. So just something to keep in mind that this can be a factor of uncertainty in ultimately what stage forecasting is for river forecast points. All these dots are streamflow measurements. So the line there is the current rating curve at the time I took the screen capture. So it was probably like a week ago. So you can see that, you know, some of the, you know, the channel changes over time too, right? So a lot of those black dots are the older streamflow measurements relating flow and stage. And so they're off from for the more recent trend, especially in the lower end of the rating curve below minor flood stage, whether the USGS is buying into the more recent measurements. But as you go out in time, or not out in time, as you go up in flow magnitude, there are less measurements. And so a good bit more uncertainty of what that flow stage relationship is. Go to the next slide. If I have one, I don't know if it's the last one. Oh, that's it. Okay. So that was a lot. Do I have any questions? Go ahead, Patrick.
Just a question about the QPF for days 7 through 14 in the HEFS. So you noted in your slide that the standard to use is the GEFS mean. I'm kind of curious if for some reason the forecaster sees some sort of significant difference between that model and, say, the EC. Is there a discretion you guys have to use a different QPF, or is the standard to use that QPF regardless of what's being forecasted in the other models?
Yeah, we don't really switch sources. For one, it takes a pretty rich set of archive forecasts to come up with those comparisons. If we had another source for days 7 to 14 that had a consistent archive of forecasts, we could think about using that. But you need a pretty decent sample size. And this goes back to what I think are some concerning things about the MBM, at least out west, is that, you know, they're making bias adjustments based on a 60-day time window. MEFP and the statistical parameterization is making, you know, I would just call them error characteristics, bias corrections, those sort of thing, based on precipitation for 10 to 15 years of data, which I think is, you know, 10 years is probably a minimum you'll probably want for or need for precipitation. So if we had a different source, for days 7 to 14 that had that sort of reforecast archive, we could use it, but we wouldn't, for example, have the capability to just switch to, say, the EC, because we would need that archive of reforecasts.
Okay, thank you. Appreciate that.
But, you know, just remember, you know, the GEFS, the spread coming out of the precipitation spread coming out of that 7 to 14 based on the GFS are not the raw ensemble members of the GFS, right? That's something totally different. It's sampling from a distribution. And so one of the reasons why we've gone that route is we think that that's a broader spread than what the actual GFS members show. This goes back to the assumption when HFS first came around in the mid 2000s, when I think the number of members in the GFS were a lot less. Now I think it's 30 something. So, you know, is 30 something members an adequate spread? I don't know. But just keep that in mind that, you know, that the spread from that 7 to 14 day period is probably different from the spread coming from the raw GFS. That makes sense.
I'll be honest with you, I'm a little bit confused by that last statement you said. So the spread from the raw GFS is different than the ensemble members.
So the GFS, yeah, I mean,
yeah.
You know, some of those spaghetti plots that Chad showed, right, of the 10-day precip accumulation and all the different members from the GFS, those aren't the members that are being input into the hydro models from the 7 to 14 day based on the GFS precip. Those are based on a single input, the mean of the GFS, and then members are then sampled from those distributions that are built based on the forecast, the mean GFS forecast of the observations over that reforecast period. So it's a statistical sampling, not a, you know, raw member of the GFS. Those are two different things.
Okay, that makes more sense. Thank you.
Any other questions for Brett or Chad? Great. Well, thank you so much, Brett and Chad. Really appreciate you taking the time to put together all the slides and present and talk about the forecasting. Like I said, we will be recording this, and so we'll have this and can share with others that weren't able to attend or were at the other 101. We are going to take a bit of a break, and then for the technical workshop, we'll be back at 1. And you actually get to hear from Chad and Brett again, and then, but in addition to with Ava and Patrick about how the forecast and observations are integrated into FIRO operations, and then with some additional talks as well. So hopefully we'll all see you back at 1, and we'll all be together in that main virtual meeting room. So see you then. Thank you so much.
Yeah, thanks for the great presentation.